In physics, we define work as a force times a displacement over which the force acts. So this is a work done by the constant force. Work done is a force times the distance moved in the direction of forces. So unit of work, units of force times the distance. For convenience, we call the Newton meter joule in honor of the physicist by that name. Find the work done by the 25 Newton force F in displacing the box S equal to 15 meter. Work done equals to force times the distance. And the work done equals to force is 25 Newton and its displacement is 15 meter. So work done is 380 Newton meter or 380 joule. If the force is not parallel to the displacement, the formula for work has a minor correction, times cosine theta. If F and S are parallel, theta equals to 0 degree and cosine 0 degree is 1. If F and S are anti-parallel, theta is equals to 180 degree and cosine 180 degree is minus 1. Finding work done by the force F equals to 25 Newton in displacing a box S equal to 15 meter if the force and displacement are parallel, anti-parallel, and at a 30-degree angle. When the angle is 0 degree, cosine 0 degree is 1. So 25 times 15 equals to 380 joule. When they are anti-parallel, cosine 180 degree, that gives us minus 380 joule. When the angle is 30 degree, then cosine 30 degree, that gives us 320 joule. Work can be negative. Find the work done by a brake in bringing a 730 kilogram of small car to a rest in 80 meter if its starting speed is 32 meter per second. The friction force and the displacement are anti-parallel. In this case, displacement to the right and friction to the left. So theta equals to 180 degree from S equals to 80 meter. And we utilize the timeless formula from our data booklets. And final velocity is 0. Initial velocity is 32. And displacement is 80. And acceleration gives us minus 6.4. And F equals to ma. Mass is 730. Acceleration is minus 6.4. That gives us a minus 4,672 Newton. And finally, we utilize work done formula, force times the distance and the angle between them. So force is 4,672 and displacement is 80, and displacement and force are anti-parallel, cosine 180 degree. That gives us minus 370,000 joule. A pulley system is used to raise a 100 Newton crate 4 meters as shown. Find the work done by the tension force T if the lift occurs at a constant speed. Free body diagram. Since the lift occurs at a constant speed, acceleration equals to 0, which means resultant force in y component equals to 0. T minus 100 equals to 0, so T equals to 100 Newton. From the statement of the problem, displacement is 4 meter. Since the displacement and the tension are parallel, theta equals to 0 degree. So use a work done formula, T times the distance moved times cosine theta. Tension is 100 Newton and the distance moved is 4 meter and they are parallel. So cosine 0 degree is 1. That gives us 400 joule. We have a two tension there from two sides. Lift occurs at a constant speed. Acceleration equals to 0. Resultant force also equals to 0. 2 times T equals to 100 Newton. Or T plus T minus 100 equals to 0. And 100 Newton is the weight. So the T equals to 50 Newton. From the statement of the problem, S equals to 4 meter. Since the displacement and the tension are parallel, and we utilize force times the distance times the cosine theta, and tension is 50, but this times the displacement is twice, 2 times 4, and they are parallel, so cosine 0 degree 1, that gives us 400 joule. Pulleys are also used to gain mechanical advantage. In this case, the advantage is 2 because the F output is the load is 100 Newton, and the force we applied is the half, 50 Newton. So mechanical advantage is 2. If we pull the spring to the right, it resists in direct proportional to the distance it is stretched. If we push to the left, it does exactly the same thing. It turns out that the spring force is given by F equals to minus Ks, and this is known as a Hooke's law. The minus sign gives the force the correct direction, namely opposite the direction of the displacement S. Since F is in Newton and S is in meter, the units for spring constant K are Newton per meter. Our force versus displacement plot for a spring is shown. Find the values of spring constant and find a spring force if the displacement is minus 65 millimeter. Pick any convenient point. For this point, F equals to minus 15 Newton and S equals to 30 millimeter or 0.03 meter. And plug into Hooke's law formula. The force applied is minus 15 Newton and the extension is 0.03, and the spring constant gives us 500 Newton per meter, which is constant for this particular spring. And we again utilize F equals to minus Ks, and spring constant is 500, and the displacement is minus 65 millimeter. Converts that into a meter, minus 65 times 10 to minus 3, and we get plus 32.5 Newton. Find the work done by you if you displace a spring from 0 to 40 millimeter. The graph shows the force of the spring, not your force. The force you apply will be opposite to the spring's force according to F equals to plus Ks. F equal to plus Ks is plotted in red. The area under the force versus extension graph represents the work done by the force. The area desired is from 0 millimeter to 40 millimeter, shown here. And area equals to 1/2 times the base and times the height. 1/2 base is 40 times 10 to minus 3 meter, which is 40 millimeter. And height is 20 Newton. That gives us 0.4 joule. Elastic potential energy shows that the energy stored in a stretched or compressed spring is given by the above formula. So we need to derive that formula. We equate the work W done in deforming a spring to the energy EP stored in the spring. If the deformed spring is released, it will go back to its relaxed dimension, releasing all of its stored up energy. This is why EP is called potential energy. As we learned, area under the force versus extension graph gives the work done by the force during that displacement. The area under the graph gives us work done. And in this case, work done, elastic potential energy, and which is equals to 1/2 times the extension times the force. And based on a Hooke's law, we also know that force equals to spring constant times the extension, and that gives us 1/2 times K times extension squared. Finally, since a extension equals to delta x, we have this formula, 1/2 times the spring constant times the extension squared. Kinetic energy. Kinetic energy, Ek, is the energy of motion. The bigger the speed, the bigger the kinetic energy. The bigger the mass, the bigger the kinetic energy. So the formula for kinetic energy is 1/2 times the mass times the velocity squared. Looking at the unit for Ek, we have the unit of mass is kilogram, unit of velocity is meter per second, but in this case is squared. That gives us kilogram m2 s minus 2, and we take out 1m, then we get kilogram ms minus 2 times m. We have a mass times an acceleration, which is a Newton, and Ek is measured in Newton meter, which are joule. What is the kinetic energy of a 4-gram NATO SS-109 bullet traveling at 950 meter per second? Solution: convert grams to kilogram, jump 3 decimal place to the left, we get m equals to 0.004 kilogram. So we need to use SI units to get a joule. Kinetic energy equals to 1/2 mass times velocity squared, and the mass is 0.04 and velocity is 950. We squared, we get 1800 joule. It's no coincidence that work and the kinetic energy are the same unit. Observe the following derivation. This is the timeless formula we learned in kinematics. Both side times mass and distribute the right side. Mass times acceleration is the net force. And both sides divided by 2. And we get final kinetic energy equals to initial kinetic energy plus the work done. Move the initial kinetic energy to the left, we get final kinetic energy minus initial kinetic energy equals to work done. And final kinetic energy minus the initial kinetic energy is the change in kinetic energy. This is called work kinetic energy theorem. It's not in the physics data booklets, and I think we need to remember this one. Use the energy to find the work done by the brakes in bringing a 730 kilogram smart car to the rest in 80 meter if its starting speed is 32 meter per second. Final kinetic energy is 0 as the car eventually stop. Initial kinetic energy is 1/2 mass times initial velocity squared, and plug in the values. 1/2 mass is 730, initial velocity is 32, and the 32 squared. Change in kinetic energy is final kinetic energy minus the initial kinetic energy. Final kinetic energy is 0 as the car stop, minus initial kinetic energy is 370,000 joule. That gives us minus 370,000 joule. And we're going to use work energy theorem, and work done equals to change in kinetic energy, which is equals to minus 370,000 joule. Gravitational potential energy: consider a bowling ball resting on the floor. If we let go of it, it just stays put. If, on the other hand, we raise it to a height delta h and then let it go, it will fall and speed up, gaining kinetic energy as it falls. Since the lift constitutes work against gravity, we have work done equals to force times the distance times the cosine theta, or force times the distance in the direction of the force. There's two forces acting on it. One is the gravitational force downward, and the force we apply to raise the bowling ball. Since the acceleration equals to 0, the applied force is equals to weight, which is mg, and the distance traveled is the height, which is delta h. Since the force and displacement is the same direction, so cosine 0 degree, and that gives us mg delta h. We can call the energy due to position of the weight gravitational potential energy, and that's equals to m times the gravitational field strength times the change in height. Consider a crane which lifts a 2,000 kilogram weight 18 meters above its original resting place. What is the change in gravitational potential energy of the weight? Change in gravitational potential energy is just mass times the acceleration due to gravity times the change in height. So mass is 2,000. Acceleration due to gravity here is we use 10, and the change in height, which is 18 meters, so that gives us 360,000 joules. Consider a crane which lifts a 2,000 kilogram weight 18 meters above its original resting place. How much work does the crane do? Tension force equals to weight, which is mg, mass is 2,000, acceleration due to gravity is 10, so that gives us 20,000 Newton. Displacement is 18 meters, so the work done is equals to force times the distance moved in the direction of the force. So force is 20,000 Newton, and the distance moved is 18 meters, which is the same direction as the force. So the final answer is 360,000 joules. Note that the work done by the crane is equals to the change in potential energy. If the cable breaks at the top, find the speed and kinetic energy of the mass at the instant it reaches the ground. We choose up as a positive reference, then acceleration due to gravity is always downward. So acceleration equals to minus g, because it's actually free falling. Use a timeless formula. Final velocity squared equals to initial velocity squared plus 2 times acceleration times distance moved. Final velocity squared equals to initial velocity is 0, so 0 squared plus 2 times, since we choose upward positives, and acceleration due to gravity is downward, which is minus 10. And since the object is moving downward, the displacement is minus 18. So that gives us 360. And the velocity equals to approximately 19 meters per second. And we plug into kinetic energy formula. 1/2, mass is 2,000, and velocity is approximately 19 squared, and we get a 360,000 joule. If the cable breaks at the top, find its change in kinetic energy and the change in potential energy the instant it reaches the ground. Initial kinetic energy is equal to 1/2 times the mass times initial velocity squared, which is 0. Is initially the box is at rest. Final kinetic energy is 360,000 joule from last slide. Change in kinetic energy is equals to 360,000 joule, and change in potential energy equals to mg delta h. Mass is 2,000, acceleration due to gravity is 10, displacement is final minus initial. So delta h is a final position minus initial position. Final position is 0. Initial position is equals to 18 meters. So final minus initial equals to minus 18. That gives us minus 360,000 joule. From the previous slide, a change in kinetic energy is 360,000 joule, and change in potential energy is minus 360,000 joules, so that change in kinetic energy plus the change in potential energy equals to 0. If there is no friction or drag, the total energy is conserved. The above formula is known as a statement of the conservation of mechanical energy. Essentially, what it means is that if the kinetic energy change, then the potential energy changes in such a way that total energy changes 0. In other words, total energy of the system never changes. Find the speed of the 2 kilogram ball when it reaches the bottom of the 20-meter tall frictionless track. Use energy conservation to find the final kinetic energy and velocity. Change in kinetic energy plus the change in potential energy equals to 0. Change in kinetic energy is a final kinetic energy minus the initial kinetic energy. And the change in potential energy is mass times acceleration due to gravity times the change in height. Final kinetic energy is 1/2 times the mass times velocity squared minus, so initial kinetic energy is equals to 0. Gravitational potential energy equals to 2 times acceleration due to gravity, which is 10. And the displacement is change in height equals to final height minus initial height. Initial height is 20 meter. Final height is 0. So 0 minus 20 equals to minus 20 meter. And final velocity is 20 meter per second. 25 kilogram object resting on a frictionless incline is released. What is its speed at the bottom? We solved this one long ago using Newton's second law. It was kind of difficult, actually. We will now use energy to solve it. Initial kinetic energy is 0. We are looking for final kinetic energy. Energy is conserved as the object resting on a frictionless incline. Change in kinetic energy is final kinetic energy minus initial kinetic energy. Change in potential energy is mass times acceleration due to gravity. Change in height. Final kinetic energy is 1/2 times mass, which is 25, and velocity squared minus initial kinetic energy is 1/2 times the mass times 0 squared as the initially at rest. Change in potential energy equals to mass 25 times acceleration due to gravity 10. Change in height is minus 6 as change in height equals to final height minus initial height. Final height is 0. Initial height is 6 meter. So final minus initial gives us minus 6. That gives us final velocity is 11 meter per second. Suppose the speed of 2 kilogram ball is 15 meter per second when it reaches the bottom of the 20 meter tall track. Find the loss of mechanical energy and its location. Use change in kinetic energy plus a change in potential energy is equal to loss or gain. Change in kinetic energy is final kinetic energy minus initial kinetic energy. And change in potential energy equals to mass times acceleration due to gravity times the change in height. We plug in the values. So half times the mass is 2. Final velocity is 15, which is 15 squared, minus 1/2 times the mass 2. Initially at rest, so 0 squared, plus 2 times acceleration due to gravity is 10. Change in height is minus 20. Change in height equals to final height minus initial height. Final height here is equals to 0. Initial height equals to 20 meter. So 0 minus 20 equals to minus 20. We get minus 175 joule. It's loss because it's give us minus sign. The system lost 175 joule as a drag and friction heat. Consider the pendulum to the right, which is placed in a position and held there. Let the green rectangle represents the potential energy of the system. Maximum gravitational potential energy. Let the red rectangle represent the kinetic energy. Because there is no motion yet, there is no kinetic energy, but if we release it, the kinetic energy will grow as the potential energy diminishes. The continuous exchange between kinetic and potential energy occurs. At the highest point, maximum gravitational potential energy. At the lowest equilibrium position, maximum kinetic energy. If the drag force is 0, then total energy is constant. So kinetic energy plus the potential energy equals to total energy, which is constant as the drag force is 0. Suppose a simple pendulum shown has a 1.25 kilogram bob connected to the string that is 0.475 meter long. That's a height, actually. Find the maximum velocity of the bob during its cycle. Assume the drag force is 0. Ek plus Ep equals to Et. And we utilize the conservation of energy formula. Maximum kinetic energy occur at the lowest point. When the bulb reaches the lowest point or in equilibrium, the kinetic energy is max. Maximum potential energy occurs at the highest point. You can see that green turns green. So change in kinetic energy is final kinetic energy minus the initial kinetic energy. Change in potential energy equals to mass times acceleration due to gravity times the change in height. So we plug in the values. Initially, the object is at rest. So initial kinetic energy equals to 0 here. Object is at rest. So initial kinetic energy is equals to 0. The change in height is final height minus initial height. At the lowest point, the height is 0. And at the maximum position, the height is 0.475 meter. So change in height is minus 0.475 meter. We solve this, we get the maximum velocity is going to be 3.08 meter per second. Consider the mass spring system shown here. The mass is pulled to the right and held in place. Let the green rectangle represent the potential energy of the system. Let the red rectangle represent the kinetic energy of the system. Then kinetic energy and potential energy is converted. A continuous exchange between kinetic and potential energy occurs. Note that sum of the Ek and Ep is a constant, the black rectangle. If the friction and drags are both 0, total energy is constant. So Ek plus Ep equals to Et, which is constant. Suppose that 1.25 kilogram mass is connected to a spring that has a constant of 25 Newton per meter. That's a spring constant, and is placed 4 meter before being released. Find the maximum velocity of the mass during its cycle. So this is maximum elastic potential energy. Then when it turns completely red, it reaches maximum kinetic energy. Ek plus Ep equals to Et. Assumes the friction force is 0. So we use conservation of energy formula. Change in kinetic energy plus a change in potential energy equals to 0. When x equals to 0 here, velocity reach maximum. Change in kinetic energy equals to final kinetic energy minus the initial kinetic energy. Change in elastic potential energy equals to final elastic potential energy minus the initial elastic potential energy. Initially, the object is at rest. So initial velocity 0. At the equilibrium or final position, the extension is equals to 0. So final elastic potential energy equals to 0. And we substitute values. 1 over 2 cancel out. And final velocity is equals to 17.9 meter per second, which is actually the velocity in the equilibrium position. If we plot both kinetic and potential energy versus time for either system, we would get the following graph.